Homogeneous functions, definition and degree. Welcome, everyone. Today we are beginning a new topic, homogeneous functions, specifically focusing on their definition and degree. Now, as you move forward into the study of differential equations, you will eventually encounter what we call homogeneous differential equations. However, before we can even attempt to solve those complex equations, there is a fundamental prerequisite. We must first master the concept of a homogeneous function. You see, understanding this concept is crucial because it allows us to recognize specific mathematical patterns within equations. Once we identify these patterns, we can use a powerful technique called substitution to transform difficult problems into much simpler, solvable ones. So, let's dive in and learn how to identify these functions. Understanding the concept. First, let's look at the basic idea. If you have a function that involves two variables, x and y, we call it homogeneous if the total power, or what we call the degree, is exactly the same for every single term in that function. So, if you're looking at a polynomial, you're checking to see if the exponents of the variables in each part of the equation add up to the same number. But as we'll see in the next slide, mathematicians don't just rely on a quick visual check. We use a more formal method. To test for this property rigorously, we use what's called a scaling factor, represented by the Greek letter lambda. The logic works like this. If you take both of your input variables, x and y, and scale them both by this same factor, lambda, and you find that the resulting function is just the original function multiplied by that same lambda raised to a certain power, then you have successfully proven that the function is homogeneous. This scaling test is the foundation for the formal definition we are about to cover. Now that we've established why we need to study this concept for differential equations, let's dive into what it actually means for a function to be homogeneous. Formal definition. A function, let's call it f of x and y, is formally defined as a homogeneous function of degree n, provided that for any non-zero constant, which we call lambda, a specific condition is met. That condition is f of lambda x and lambda y equals lambda raised to the power of n multiplied by the original function f of x and y. To make sure we are clear on the components of this formula, lambda represents our scaling constant, the factor we use to expand or shrink our variables, and the letter n represents the degree of the function, which is the specific power that lambda is raised to. Now that we have a general idea of what it means to have a consistent power across a function, let's look at the formal mathematical definition. This is the precise rule you'll need to use when solving problems. In the next slide, I'll show you an alternative way to represent this same concept using ratios. But for now, keep this formula in mind, as it is the primary tool you will use for the step-by-step verification process we are about to see in our examples. Alternative representations. Now that we have covered the formal definition using the lambda scaling test, I want to show you an alternative way to recognize these functions. This second method is actually a very powerful tool, especially when you move forward into solving differential equations. Essentially, a function can also be identified as homogeneous of degree n if you are able to rewrite the entire expression in terms of the ratio of the two variables. To put this into mathematical terms, a function, f of x and y, is considered homogeneous of degree n if it can be expressed in one of two specific forms. First, it could be written as x raised to the power of n, multiplied by a new function, let's call it g, which depends only on the ratio of y over x. Alternatively, it could be expressed as y raised to the power of n, multiplied by a function h, which depends on the ratio of x over y. The key thing to remember here, and this is crucial, is that in these expressions, the functions g and h don't care about the individual values of x or y on their own. They only care about the relationship between them, specifically their ratio. As we will see in the next few slides, being able to view a function through this ratio lens is often the secret to simplifying complex problems. Real-world analogy, geometric scaling. Now, I know that the formal definition using lambda might seem a bit abstract, So let's step away from the algebra for a moment and look at a real-world analogy to ground this concept. Think about what happens during geometric scaling. Imagine you are working with a simple formula for the area of a rectangle, where the area, A, is a function of width, W, and length, L in its simplest form. The area equals width times length. Now, let's apply the scaling test we discussed in the previous slides. Suppose we scale both the width and the length by the same factor, which we will call lambda. If we replace our original width and length with lambda W and lambda L, our new area calculation becomes the quantity lambda W multiplied by the quantity lambda L. When we simplify this expression, we multiply the two lambdas together, which gives us lambda squared, and then we are left with the original width times length. Because our resulting expression is exactly the original area formula multiplied by lambda raised to the power of 2, we can conclude that this area function is a homogeneous function of degree 2. This isn't just math on a page, it mirrors how we experience the physical world. For instance, if you take a two-dimensional object and double its dimensions, meaning you use a scaling factor of 2, the area doesn't just double, it increases by 4 times, which is 2 squared. This perfectly illustrates the principle of homogeneity that we are about to apply to more complex algebraic functions in our next examples. Step-by-step examples. Let's look at example 1, where our goal is to verify if a specific function is homogeneous, and if so, to identify its degree. The function we are examining is f of x comma y, which equals x squared plus 3xy plus y squared. To do this, we will use the lambda test we discussed in the previous slides. Step 1. We begin by replacing every x with lambda x, and every y with lambda y. When we substitute these into our function, we get f of lambda x comma lambda y, which equals the quantity lambda x, all squared, plus 3 times the quantity lambda x, times the quantity lambda y, plus the quantity lambda y, all squared. Step 2. Now we need to simplify those powers. Applying the exponent to the terms inside the parentheses, we get lambda squared x squared plus 3 lambda squared xy plus lambda squared y squared. Step 3. Notice that every single term in our expression now contains a lambda squared. So, we can factor out this common term, lambda squared, from the entire expression. This leaves us with lambda squared multiplied by the quantity x squared plus 3xy plus y squared. Step 4. Finally, we compare this result back to our original function. You'll see that the expression inside the parentheses is exactly our original function, f of x comma y, because we have shown that f of lambda x comma lambda y equals lambda squared times f of x comma y. We can confidently conclude that this function is homogeneous, and its degree is 2. Now that we have covered the formal definition and the theory behind scaling, let's put it into practice with our first concrete example. This successful verification sets the stage for our next example, where we will see what happens when the powers do not align. Step-by-step examples continued. Now, let's look at a contrasting case in our second example. In the previous slide, we saw how a function could be homogeneous when all terms shared the same power. Here, we are going to identify a non-homogeneous function. Our goal is to determine if the function f of x comma y, which equals x squared plus y, is homogeneous. To do this, we will apply the same lambda test we used in example 1. Step 1. We begin by replacing every x with lambda x, and every y with lambda y. When we substitute these into our function, we get f of lambda x comma lambda y, which equals the quantity lambda x all squared plus lambda y. Step 2. Next, we simplify the powers. Squaring the first term gives us lambda squared times x squared, so our expression becomes lambda squared x squared plus lambda y. Step 3. Now, we attempt to factor out a single power of lambda from the entire expression. If we try to pull out the largest possible common factor, we can factor out a single lambda. This leaves us with lambda multiplied by the quantity lambda x squared plus y. Step 4. Finally, we reach our conclusion. Look closely at what remains inside the parentheses. It is lambda x squared plus y. This is not the same as our original function, f of x comma y, as you can see, the powers of lambda are inconsistent. The first term has a power of 2, while the second term only has a power of 1. Because we cannot factor out a single lambda raised to a power n to recover the original function, we must conclude that this function is not homogeneous. This leads us perfectly into our next slide, where I will highlight some common pitfalls to avoid when performing these calculations. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. As we've seen in our previous examples, identifying homogeneity requires precision, and it is very easy to trip up on a few specific details. First, let's talk about ignoring constants. This is a very frequent mistake. When you see a lone constant, like the number 5, don't just treat it as a separate entity. Remember that mathematically, 5 is actually 5 times x to the power of 0. Because of this, if your function contains a constant term that doesn't have a variable attached to it, the function will usually fail the homogeneity test, unless the degree of the function happens to be 0. Second, be very careful with incorrect power factoring. When you are performing the lambda test, replacing x and y with lambda x and lambda y, you must ensure that you can factor out the exact same power of lambda from every single term in the expression. As we saw in example 2, if you end up with lambda squared in one term and just lambda to the power of 1 in another, you cannot factor out a single, uniform power. If even one term doesn't share that same power, the function is not homogeneous. Finally, there is a subtle but important distinction you must keep in mind. Do not confuse function homogeneity with equation homogeneity. Up until now, we have been focusing on whether a function itself follows the lambda rule. However, when we move into solving differential equations, we say a differential equation, where the derivative by dx equals the function f of x and y, is considered homogeneous only if that underlying function, f of x and y, is a homogeneous function of degree 0. Keep these distinctions clear in your mind as we move into our final summary. Key takeaways. All right, we have reached the end of our lesson. Before you move on to practicing these problems, let's quickly recap the key takeaways from today's session to ensure you have a solid foundation. First, remember the lambda test. As we saw in our step-by-step examples, the most reliable and foolproof method to check for homogeneity is to perform a substitution. Simply replace x with lambda x and replace y with lambda y. If you can successfully manipulate the expression to look like the original function multiplied by a power of lambda, you have proven it is homogeneous. Second, let's identify the degree. Once you have successfully factored out lambda, the exponent attached to that lambda is exactly what we call the degree, or n, of the function. Third, keep the ratio form in mind. This is a crucial concept for when we begin solving differential equations. Remember that any homogeneous function can be rewritten so that it depends only on the ratio of y over x, or x over y. This transformation is what allows us to use substitution to simplify complex equations. Finally, always look for consistency. For any polynomial function to be considered homogeneous, every single term must have the same combined power of its variables. If you see even one term where the powers don't match, as we saw in our second example, the function is not homogeneous. Review these points carefully, and once you feel confident with these definitions, you'll be well prepared to tackle the actual differential equations in our next lesson.